Great.
Yeah, go ahead.
Thank you. Thank you for the nice introduction. And I'm honored to have the opportunity to share my insights into the challenges and opportunities of quantum computing system designs. And here is outline of my talk. And given like quantum computing has already been there for more than 40 years, like in this talk, I will introduce like why this is a good research topic for us, especially from the computer scientist perspective, and what will be the important research topic in the next 5 to 10 years. And then I will focus on my quantum computing system research, and because it is a pretty new field from the systems perspective, I will mostly like focusing on the formulation of the research problems instead of the detailed solutions. And especially, I will tell you like about like what are the interesting interplay between the classical research system, like computing system and quantum computing. So if you are new to quantum computing, but you have expertise in classical computing systems, you may see there are a lot of things related. And toward the end of the talk, I will provide a brief overview of my work on machine learning system, which is another important part of my research. So first, why now? I think one of the big reasons is a rapid development of quantum hardware, which has far exceeded expectations. And here in this figure, I show like the recent development of quantum hardware, especially we show the number of qubits in the quantum hardware. And you can see like it has grown significantly over the past years. And especially for a long time, say from the 1998 to 2015, over the 17 years, there is only hardware with a few qubits that can be only accessed in the lab. But if you look at the last 7 years, we now have cloud accessible quantum hardware with hundreds of qubits. So even you are only work from home with your own computer, you can still get access to many of these machines and run your experiments remotely. I think that's already show like how computer science and physics can help each other. And it's also mentioned that in the next few years, we can increase the number to 1 million qubits. So if you decided to join the field, you may wonder what are the parts that computer scientists can contribute to quantum computing. And to answer that question, it's important to know that quantum computing has been around for already 40 years, and the past can provide valuable insight into the future. And let me give you like a brief overview. And the first wave of quantum computing starts in 1983, while the concept of quantum computing was first generated. And researchers at that time tried to find quantum applications that can show like practical like quantum speed up. So mostly like theory guys and algorithm guys. And they assume that one day, like we can just build this ideal, like no noise, large scale quantum computer. And they have achieved like great results. And in general, we could expect exponential speed up on applications with quantum data, like physics system simulation, and also applications with classical data, but with hidden structures like the integer factoring algorithm. So it all sounds perfect. But soon, like experimental scientists find that the noise on the quantum devices could be much larger than that on the classical devices. Even nowadays, the quantum, this kind of gate error can be about 1% or 0.1%, and which is almost like 10 orders of magnitudes higher than like what we have in classical computer. And such error is hard to be removed at pure physical level, and that lead to the second wave, where people started to prove like whether we could still have the quantum speed up. We proved in the first wave, if one day we can only build this kind of noisy but still larger scale like quantum computer. And the good news is yes, and we can fix the error. And the key enabler here is a quantum error correction code. And the quantum error correction series does not only tell us if the error rate per gate or per time step is below a threshold. So then we can having like non-reliable quantum computers. It also tells us that this kind of overhead for applying error correction code is also tolerable, and especially for those applications with exponential speed up. And if your applications only show quadratic speed up, then maybe this kind of error correction overhead could be a concern. So again, like we have, it seems that we have like resolved all the major issues in quantum computing. But soon, like people find that, okay, if we really want to show this kind of practical speed up, okay, using experimentally, we still need to have minutes to billions of qubits. And that's a lot of money and engineering efforts. So imagine that you go to investors and say, okay, give me like $2 million or $10 billion. And maybe in 20 years, I will give you a machine and show, okay, we can do it. So no one will give you the money. And that's not the world is working. So that's why like people are trying to find more like near-term milestones so that we can have more confidence in quantum computing. That lead to the third wave, and the third wave is try to experimentally prove we can like use quantum computers for something that is better than the classical machine. And here, like we want to directly use what we have now, the machines we have now, so they are both noisy and also small. Okay, but good news is, yes, we can show it. And there are a series of quantum advantage experiments being shown in the last few years from Google, from USDC, and from Xanadu. But and I have to emphasize here, so I cross out this kind of practical because usually like when we show this kind of experimental like advantage experiments, we are not working on some practical applications. Instead like working with some computer serial guy, try to design some computation that is like super hard in terms of the complexity. So like to summary, in summary, the current status is like we can already show like quantum devices have great computation power, even compared to the best classical devices we have today. But it's not yet for those practical applications. So what would be the next? I think from the history, it's pretty clear. So one clear goal is try to have this kind of practical speed up for some practical applications. And to achieve that from the history, I feel like at least like we have 3 key tasks. So the first task is follow the wave 3, seeing like we only stick to NISQ machine, okay, without the quantum error correction code. So like the key insight here is we are not fully utilizing the full power of the NISQ machine, and maybe with some algorithm and hardware co-design, we can tap its full potential and really achieving something amazing. And the second like research direction, I think, is following wave 2. So it's possible that we only can achieve quantum practical speed up when we have error correction protected machine. And then the question is how to enable this quantum error correction protection, especially like with limited computation resources. And no matter we go with wave 1 and wave 2, or like wave 2 or wave 3, these first 2 tasks, we always need to scale up our machines to including like more qubits in the system so that we can compute like increase its computation power. So these are the like 3 tasks in my mind that will be crucial for future quantum computing. And what is our role? I think there are a lot of things we can do as we have decades of experience in optimizing our classical computer and tuning it for different practical applications in a most cost-effective way. And I believe our expertise matches perfectly well with this new wave. So especially I want to highlight the 2 important roles for us to play. And the first role is more like a sporting role. And my insight is like one way our hardware get more and more complicated, we also need to have a very like complicated and also like a smart, intelligent software stack to fully harness the power of the hardware. And here I give an example in classical computing, and it is for matrix multiplication, which is a really simple like computation kernel. And we show that if you are like the performance difference from using an interpreted language Python to a compiled language like C, and with a few like optimization flags being enabled, you can see that the performance difference can up to like a few orders of magnitudes. And we envision like similar things can happen to quantum computing. And here, like I just want to show another like recent example, like from IBM. And it's on the left hand side is an IBM Q mature machine, and on the right side is a quantum circuit they want to run. As quantum circuit is very noisy, so it will we do not apply like the software optimization. The larger the circuit we can run with meaningful result is a great part. And you can see like when we enable the software optimizations, the circuit we can run can be much larger. And the data is from our collaborator from IBM. And our insight is nowadays the quantum devices is still like quite simple, but once the device is getting more and more powerful, we envision it will be also more and more complicated. And what we have in the previous slides with orders of magnitudes difference could happen here too. So which like really calls for a great like software stack. And the second role in my mind is more like a leading role. So I'm a little bit ambitious here. I feel like even we are doing this kind of system optimization with like we can still be the having a leading role, like working together with other scientists. And the reason is the huge design space for future like quantum computing technologies. Even we have envisioned that we can build 1 million qubits on our device, it's not clear like how to go there and what is the most cost-effective way. And our feeling is usually the best way requires like software hardware co-design. And only after we understand what can be done from the software side, we can guide the hardware guys try to focus on the most important parts. Okay, and here I also want to draw example in classical computing. And if we only from the physical level, like we may want to like find a perfect memory that is simultaneously cheap, large, and fast. But the memory hierarchy tells us that we do not need to do that simultaneously. Actually, we can do some decoupling of the function so that we can have a better cost and design flexibility, and that also like requires like the compiler and the computer architecture co-design. And that also like in my mind, I think the future quantum computing could be also this kind. In particularly, I want to mention like nowadays the quantum devices still like envision this kind of horizontal scaling, meaning that we want to pack more and more qubits onto the same chip. And the working style for quantum computing is more like what computing in register style. So we do not really even have this kind of memory hierarchy. We do not have this kind of memory cache or really this kind of disk concept in quantum computing. And like the qubits here, both storing is for storing the information and also for the computation itself. So my invention is it's possible that we can borrow this kind of memory hierarchy idea to build this kind of hybrid computing. And one of the insights, for example, is superconducting. They have like faster gate time, so it may be working as our register. But on the other side, they also have like super low like coherence time. In contrast, like ion trap neutral atom, they have longer coherence time, but their gate time is lower. So maybe they can work as our like memory and cache. On the other side, the photonics usually is a key enabler when we want to convert want to combine different kind of quantum technologies together. And they also can work as this kind of quantum interconnect. And I envision this kind of scaling as this kind of vertical scaling as a better way for us to build even like one QPUs. Okay, so to this end, like here gives an overview of my quantum system research. I think it exactly follows my vision. So like on the left-hand side is the classical system stack, which has been working on for many years. And on the right-hand side is the key, like 3 key quantum related tasks. I feel like that is important for the next few years. And after working on this kind of research for a few years, I found that a lot of classical high-level philosophy still works, and it even like provides a direction for optimization. But if you want to work on quantum computing, you have to understand the details because the low-level abstraction and the solutions will involve. And I'm also like very proud as our group as the first few like looking at the second and the third task about the scaling up and also QEC protected quantum computing, and we believe that as a future in additional to the NISQ computing. And thanks for our collaborators, we have achieved a list of publications, and most of our work is being integrated into their industry platforms. And for this talk, I will mostly focusing on our compiler work due to the time limit, and emphasize on the unique challenges it presents in quantum computing. And here, let's start with our compilation work for NISQ machines and see what kind of philosophies do apply and what new abstractions and solutions are devised. So first, let's look at how a quantum program look like. As quantum programming is at pretty low level, quantum programs are also called quantum circuit. And the example program here contains 3 qubits and a few gates. And the quantum gates are directly governed by underlying quantum mechanics, and thus they are different from normal classical gates. And that is also why it's called quantum computing. Here, the HATMAT and the Z gates are operating on 1 qubit, so they are also called 1 qubit gate. One qubit gate. And the 2 qubit gate are similar, but it's applied to a pair of 2 qubits. This kind of low-level gate programming also serves as a good abstraction for hardware engineering. So no matter you are working on ion trap, photonics, or superconducting, as long as, for example, you are physics, as long as you can show your hardware can enable this kind of 1 qubit gates and some 2 qubit gates, you can say my hardware is universal, it's general to be used for any quantum applications. But there also comes one limitation, that is this kind of qubit level addressability. So usually when we write our program, we assume that the 2 qubit gates can be applied to any pair of qubits. But on real hardware, that's not the truth. And in fact, we usually have the limited direct 2 qubit gates, and it's a common physical constraint that exists in different kind of quantum hardware. And here I just use IBM's 5 qubit superconducting chip as an example. So the transport qubits are marked in yellow, and they are this kind of dark square. And to enable 2 qubit gate, we must physically connect them with a resonator marked in red here. And because of different connection constraints like frequency collision, crosstalk, and 2D wiring, only some pair of the qubits are directly connected. And this kind of connection constraints can be abstracted in the coupling graph on the right-hand side. And you can easily tell whether a 2 qubit gate, like a CNOT gate, can be applied by examining the edges between these different nodes. For example, if you if we want to apply a CNOT between Q0 and Q1, you find they are connected, it's fine. And because there's a resonator on the hardware. But if you want to apply a CNOT gate between Q1 and Q3, there's no connection between them. That also means there's no resonators connecting Q1 and Q3, so you cannot directly do that. So now it become a compilation problem because there's a gap between the programming and the real hardware. So on programming, assume any 2 qubit gates can be applied to any pairs of qubits, but on the hardware, there's no direct connection. So this gap can be solved by a compilation path called qubit mapping, and this part is very similar to the classical register location problem, but there the limitation is the constraint is a limited number of registers, and here the constraints is a limited number of connection. And here I just want to use another concrete example to show you how this kind of things happen. And on the left-hand side is a quantum machine, with 4 physical qubits, and it's not fully connected. It's only fully connected. You need to have 6 edges, but now you only have 4 edges. And on the right-hand side is one quantum program we want to run this machine. And suppose we are going with some initial mapping here, and we can say, okay, the first gate is executable, so it's the second gate and the third gate, but the fourth gate is not executable because they are not directly connected on your hardware. So and similar is a 6th gate. And to resolve that issue, one of the ideas is to do a remapping before like the non-executable gate. And for example, here, just before the fourth gate, we can try to do a remapping between Q1 and Q2 so that now like all the remaining gates can be executable. And because of a lot of quantum constraints, and to do this kind of remapping actually requires to insert a special like swap gate. While the swap gate tends to be very noisy, so it's like if you want to run your original program, you have to insert a lot of actual instructions just to make it compatible with the hardware. And it turns out to be an incomplete problem to minimize the swap gates. And one of the reasons is there are many places you can insert the remapping. And for each remapping, you can find different ways just to resolve one of the next like non-executable gate, or more global, try to resolve a lot of like gates, non-executable gates in the future. So it has this kind of nature of like NP problem. So instead of having the details, I just want to tell you, okay, our cyber compiler is provide a very efficient heuristic to solve this kind of issue. And here just to show like overall result, you can see like compared to the state of the art at that time, which is mostly exhaustive search methods, our compilation time or the search time is much shorter. Like we can provide 1,000 times speed up for the compilation. And what is even amazing is like our generated program is also better. And we can save the number of swap gates to be inserted by 10% compared to the state of the art at that time. And I have to emphasize here, like reduce the number of gates by X percentage is the same as reduce all physical gate errors by X percentage. And so that's why I say like software people can achieve similar things as the physics people who really working on the hardware, and like try to understand what can be achieved from the software side really tell us like what is needed from the hardware part. And our work is also served as a default mapping methods in IBM QuickSCAD and many other quantum compilers as listed here. So like, but that is not enough. So as a compiler person, like I always wonder, can we do better? Because in classical build, like optimization as the machine code is usually like the last step we apply. And this kind of 1 qubit and 2 qubit gates in quantum is almost like the machine code in classical computing. So we wonder like, can we really like having this kind of high-level structures, just like the loop structures in classical computing, so that we can apply a lot of high-level optimizations. That leads to our like polyhedral compiler in ASP+ 2022. And especially like our polyhedral compiler provides the first formal high-level intermediate representation that is try to capture this kind of larger scope quantum informations in quantum programs. And it works because it's you may want to know like what kind of high-level structures you can have in a quantum program. And actually, it is just some multi-qubit gates kernels, but it is not general multi-qubit gates, but a special types of many qubit gates. And here, just to give you an example, like showing how can we have like a set of like many qubit gates to present your program, and each of these kind of multi-qubit gates can be like decomposed into this kind of 1 qubit and 2 qubit gates, which is natively supported by the hardware. And this process is more like loop unrolling process, because like how we like the way we choose like the special types of the many this kind of gate set. And it also enables a lot of optimizations. And as shown here, if you look at these two like many qubit gates, you may find that a lot of parts of them are similar. Okay, the only difference happens in the last gate. So if you notice this kind of high-level information, actually can coordinate this kind of lowering to 1 qubit and 2 qubit gates and make do a co-synthesis together. And indeed, in this way, you can save almost like 50% of the gates in the final generation. And it's more like a loop fusion process. And here just to show like the result. And actually, like the result is pretty nice. So we conducted experiments on like both superconducting like architectures, which is a coupling graph is very sparse, and also like for ion trap like architectures, which is more like sparse, like dense locally but still sparse globally. And you can see like we can reduce both the number of gates and the depth by almost like 50%. And because like we are enabling this kind of high level optimization, like compared to the single pass optimizations in the previous work, we are having more compilation time, but it's only 5%, so it's tolerable. And we are also like happy that like our polyhedral compiler is being adopted by IBM's QuickScape and Amazon Bracket, and is in especially like previously it's mostly like only one level gate level optimization, but now like if the applications follow our specifications, it can go to a high level optimizations first and then go to the low level optimization. So I think it just does the first step because like in classical computing, like we have multi levels of intermediate representations to abstract our program and enable a lot of optimizations. And try to enable the same things in quantum computing, we really need to understand our application better. And that requires working with the domain experts, try to find this kind of high level abstractions. I think there are a lot of research opportunities here. Here, I just another thing like we have been doing, I think is pretty interesting is we also not I have to say like superconducting and ion trap, they are solid state qubits, so their software infrastructure are kind of similar, but photonic or quantum computing is kind of different. The reason is like photons do not like to interact, and thus it's very hard to perform this kind of two-qubit gates, and thus a different kind of programming model is needed instead of the gate-based circuit model. And you can see here on the left-hand side, each of these gates become a set of measurements, okay? Single qubit measurements on the right-hand side, okay? And so you can see like when we have a different programming model, then you definitely need to have a new compiler built for it. And especially there is also some like gap between the programming model and the real hardware. And one special thing here is usually when we have this kind of new measurement-based quantum computing model, we assume that we can build a large entanglement states. But on the hardware, it's not true. Usually on real quantum hardware, on photonics hardware, each time we can only generate a small resources state with a few like qubits. And if you want to generate this kind of large entanglement states, you have to do this kind of fusion. And the fusion is just like the two-qubit gates in the gate-based model, which is very costly and noisy. So that's why we also need to have a compiler to make a solution to mitigate the gap between the high-level programming model and the low-level hardware constraints. So if you are interested, I recommend you to refer our paper for more details. So now let's start with the compiler for to say like how compiler can help with this kind of error correction code integration. But let's first want to understand why we want to have error correction code. So we mentioned this concept a few times, but I still want to give you a concrete idea. The general reason is definitely like quantum hardware is very noisy, but taking IBM the Washington machine as an example, the signal error is about 1%, and that with that kind of error ratio, if you have a program with about 70 signal gates, the final fidelity of your program is about 50%, meaning that only have 50% you can get the correct results. For the other like 50%, you will have random results. Okay, you can see like when you have more signal gates in your program, basically your correct result can be buried in the random noise. So like quantum error correction code is try to protect our program running on this kind of noisy machines. And the key here is try to introduce this kind of redundancy, in particular, introduce a quantum way to compose multiple physical qubits of this kind of high ratio, noise ratio into a one logic qubit with less ratio, less error ratios. And here, like I want to use a surface code to give you a more concrete idea. And indeed, a surface code is one of the best QuCS code with great error correction capability and mild hardware locality requirement. And when the surface code was first designed, it assumes that one day we can build this kind of 2D hardware or like quantum hardware, especially like each of these kind of qubits are directly connected to 4 like neighboring qubits. And here, like just to give you a more like concrete location about like if we want to build a distance 3 surface code. And for this distance 3 surface code, you can see in total, if you count it, it's 25 like total physics qubits, like 5 times 5. And in particular, like there are 13 like blue data points. And these 13 blue data points are used for storing the information. And in addition, we have 12 ancilla qubits. And this 12 ancilla qubits is for checking the parities, okay? And if there's error on the data qubits, then the ancilla qubits will be lightened and you will know there's an error here, you can do the correction. And you can see like in particular, the freedom here is just 1 because you have 1 more data qubits than the ancilla qubits. That is how in total, these 25 physical qubits working as 1 logic qubits. And definitely you can increase the distance D here, like try to, for example, this one is a distance 5, like surface code. And in total, you have 81 like data qubits, 81 physics qubits, well, like 41 is a physics qubits and 40 is the ancilla qubits. It's still working as 1 logic qubits, but it enables like more or better protection. And one of the recent paper from Google is trying to show, okay, so when you increase the distance, meaning you are adding like more physics qubits to building 1 logic qubits, you can have like more error protection power. So it all sounds perfect, but there's a mismatch between the surface code and the sparse architectures, the real hardware we can build today. So I have to say like when the first surface code was first generated, I think this kind of 2D lattice assumption is reasonable. Okay, it doesn't really sound very demanding, but it turns out in reality, it's not that case. And actually, like nowadays, only Google has this kind of 2D lattice structure, but it still has a great issue with this kind of fabrication yield when you want to scale up your machine. And IBM has followed the same 2D lattice at the beginning, but later they try to convert it into sparse architecture because of this kind of hardware constraints. And you can see here, the architectures, for example, for this qubits is only connecting to 2 neighboring qubits, and for this one is only to 3 neighboring qubits. So it has a sparse architecture. So one question is here, like when we have this kind of sparse architecture, like how can you do? Like do you really need to like design a new like error correction code for them? And actually, a lot of IBM like domain experts is trying to manually design new codes that is tailored for this architecture. But as a system person, is that really necessary? Sometimes we feel like a non-perfect match usually is the best solution, just as a memory hierarchy, okay? And it's possible like it could be more cost effective. And to this end, we wonder, can we use a compiler to mitigate this kind of structural level mismatch? And and our ASCA 22 paper, the surface stage is just the first like automated framework, try to compile like surface code to different sparse architectures. Instead of giving you the detailed solution, I want to give you some insights about why this can be done and why it is challenging. So first, why this can be done is you have to take quantum error correction code as a approximate algorithm, because the key idea is try to introduce the redundancy. So you can actually you can try to insert more redundancy or try to get away some more redundancy as you like, okay? So it will not fail like immediately, okay? And especially here gives the example. So instead of using 1 ancilla qubits to get the parity of 4 data qubits near like around it, you can use 2 ancilla qubits, each of them getting the parity from its like 2 neighbors, and then like we can merge this kind of parity information together. So this this kind of change actually like lowers the demands for 1 like 40-way qubits into like 2 30-way qubits. So in this way, you can relax this kind of degree constraints. But why it is challenging? The challenging because first we have a large queuing space, especially when like you are looking for a large distance code. There are a lot of qubits there, and there are different ways you can do this kind of tuning. So what is the best way to do it is kind of challenging. And the other thing is, usually like when you are working with error correction code, you have to think about the logic qubits built upon it and how we can enable this kind of fault tolerance when we execute our real program, and that will make things a little bit challenging. And especially you can say like error can propagate and accumulate across different iterations. For example, here, and the errors first propagate to another zero qubits and finally propagate to all data qubits. That is something we really want to avoid. Otherwise, this kind of error protection power can be much lowered. So these are all the things we need to consider when we really design the surface code or like relax this kind of surface code to different sparse architecture. So the good news is, okay, we do succeed and our result is pretty amazing. And sorry, maybe here. Okay, so first, if you look at this kind of heavy hexagon structure, these two yellow bars, you'll find that we work as the same as the domain experts. Okay, we compare to the manually designed code from IBM's domain experts for these two architecture. And in our paper, we have other results. And for the blue one, the heavy hexagon, like we are twice better. So our insight here is for heavy hexagon, it's very much like the 2D lattice structure. So that's why human being can easily explore the design space, okay, when the design space is small. But for the heavy hexagon, because it's very different from the 2D lattice structure, actually it involves a large design space. And my feeling is when there's a larger design space, human being cannot do it very well. So we need to rely on this kind of compiler to do an automatic search. So that's why I'm saying, okay, so human beings should focus on this kind of abstraction while letting this kind of compilation tools to do this kind of search for automated for us. And I also want to mention some people may feel, okay, with physics people improve their hardware. Maybe one day we can directly make this kind of 2D lattice structure. Then your framework is not useful. But I have to say that is not the case. Even you can make this kind of 2D lattice structure, it's possible that some of the qubits are failing. And the ratio could be high sometimes, okay? So that will lead to a non-perfect 2D lattice structure. And our compiler can still handle that. So generally speaking, I think our compiler really built this kind of first infrastructure for QuCS development. And our conclusion is only after you assess the existing, the power, the capability of existing like error correction code, like the surface code, you make enough argument for making new error correction code. Okay. And we believe the future QuCS development could be a general like compilation problem. And in this work, we only focus on the surface code, but there are a lot of other different stabilizer code, subsystem code, and their hybrid concatenation and combinations. And we believe a compiler could be the first like infrastructure for us to assess their effectiveness. And we also believe, okay, potentially like code design with this kind of like QuCS code towards your hardware could be a better solution. That requires to working directly with the physicists to understand which part can be tuned, which part cannot be tuned. And for near term, if we really want to enable this kind of infrastructure for some like killer applications, it's also possible to do application QuCS and hardware co-design, and that requires to work together with a series. So a lot of things to be done here. And the last part is try to show, okay, compiler can also like do a great work for distributed quantum computing for like final scaling up. So why we want to have distributed quantum computing? And our first argument here is DQC could become the major test bed for run many larger scale quantum programs in the future, and especially for those applications that requires millions of qubits to be there. And one of the reasons is like scaling like quantum devices monolistically is very challenging. Like compared to the classical computer, we can easily like pack billions of transistors onto the device, onto the chip. In quantum computing, it's much more difficult. For example, for IBM's like superconducting devices, they can only like even though the chip is small, they can be only operated in a refrigerator at a low temperature, while the superconducting property can be manifested. And that requires like really good control of the heat dissipation. But if you have like a lot of qubits, then you have to connect a lot of cables to control these qubits. And then this kind of cable heat dissipation could be the killer for us to scaling up. So that's why like we are envisioning in the future, especially like we want to build a machine, we may want to have a DQC-like architecture. This DQC could be real like distributed machine, like for example, connecting like several refrigerators in the room, or even like chiplet designs, or like even a real like distributed over several different states in the United States. And here you can see like as long as we can enrich each processors with 1,000 qubits, and possibly we can connect 1,000 node together using the kind of quantum internet network, and then we can build a machine with 1 million qubits. Okay, so in this way, like the DQC allows both intra-node scaling and inter-node scaling, and it's possible for us to even connect machines with different companies or different technologies together. Okay, so that enables another level of scaling. And so like, suppose we have the DQC machine. The first question is, how can you run your program on it? And here, just to give you an illustrative example, and suppose like our program has 3 data qubits, and now you have 2 machines. Each of them only have 2 qubits. How can you run it? And one general idea is try to partition the circuits. And one of the idea, like things we want to optimize is this kind of internode communications or internode gates, remote gates. And then like when you having abstracted this kind of remote CNOT gates, you just need to plug in the optimal implementations for each remote gate. And here just to like give you further information about the implementation of the remote operations in DQC. And suppose like now we have 2 nodes, Q1 and node A and node B, and you want to enable a CNOT gate between Q1 and Q1 prime. And because they are not directly connected, you cannot shoot a pulse, for example, onto the resonators, connecting them just like what we done locally for a superconducting device. Instead, you are requiring with 1 spatial qubits called communication qubits. As the communication qubits will emit EPR pairs, for example, through the optic fiber. And this EPR pair will working as a virtual channel between these two nodes. And after you have the virtual channel, you can like execute this kind of remote CNOT gate. And the first part is called cat entangler. You don't need to understand the details. I block them intentionally because they are just some local gates and classical communication. So which we know like how to do effectively very well. And after cat entangler, it seems like we have a copy with a Q1 onto the node B now. And now like you can do the CNOT gate. And then like we can enable a cat entangler to move the Q1 back to node A. And I have to say here, like one of the most important resources we consume here is the EPR pair, the virtual channel. And each data movement will consume 1 EPR pair generated by the communication qubits. Another thing is this kind of communication qubits you can see are also occupied for the duration of the remote communication. So if you want to do another remote case, you have to let the communication qubit generate another EPR pair. So, and it turns out that this kind of process is a major issue that could lead to the bad performance of DQC. And especially EPR pair generations requires like super long time and low fidelity compared to the local ones. It can be 10 times to 15 times worse. Okay. Another thing is on the right side, you may notice that if you want to have multiple blue qubits communicating with each other, that can be bottlenecked by the limited number of communication qubits on each chip, because the communication qubits is also part of the computation. So to this end, like sorry, like here, I just want to show like there are some work for DQC, but their focus is only for the better prediction, try to minimize the number of remote signal gates. And our point is, can we do better? Okay. And our work is try to enable this kind of connective communication compiler for DQC. And our key insight here is, if you look at these individual remote gates, then almost like the previous work is doing their best, okay? But actually they are not independent. A lot of scattered communications are doing some global function together. It's very similar to the all-reduced function in the classical computing. So if we really leverage their global structure, we can do much better and substantially reduce the number of communications we need, or the number of EPI pairs we need to enable this kind of communication. And our contribution is a very general DQC compiler for enable this kind of communication, connective communication. Especially I want to emphasize one of the key enabler in our design. This is this kind of quantum communication buffer, because if we want to have this kind of connective communication, usually we need to have more communication qubits into play. But as I mentioned before, quantum communication qubits can be very limited. And one of the insights we find that is, actually, like there are two functions that communication qubits are playing. One is to generate the EPI pairs. We find it's a master requirement, but part of the communication computation is not necessary. To this end, we are trying to do a decoupling of these two functions and using a cheaper data qubit as a virtual communication buffer for the computation itself. Okay, it's very similar to the memory hierarchy idea. So here, just want to give you a concrete example. So when we have only one pair of the communication qubits, we can only emphasize let it focusing on this kind of EPI pair generation. Once it's generated, then like we can do a swap gate and change this kind of information into our local communication buffer, which are made of the data qubits. Okay, and I also like our compiler also let you to automatically decide the best buffer size according to your input program. As like you can see, it's not always where having a large buffer is better, because if you have a larger buffer, it also means you have lesser data qubits on your node. And when you have a you have a program to execute, that could lead to like more nodes for the execution and more communications there. And in our paper, we have more optimizations. And here, just want to give you the final result. And we compare our DQC setting with a single monolistic quantum chip there and a set of benchmarks. And we compare we use two metrics. One is overall fidelity of the program, and the second one is the latency of the program. So ideally, so if you have a perfect DQC, then you have like unlimited number of communication qubits, and the remote EPI pair is just the same as a local communication, then you will have this curve. Okay, it's the same as having DQC and local large single chips. But if you look at the previous DQC compiler, you will find that, okay, it's much worse. As long as you have more nodes, usually you have more communications, and it will be directly becomes a communication becomes a performance bottleneck. And actually, like from this curve, you may think, okay, perfect DQC hardware is really needed. So we really want to like lower the communications, like just as a similar level as the local communication. But that hardware solutions will be very costly. But if you look at our DQC compiler, the performance is almost like much better. It's much more close to the ideal scenario. And one of the reasons is we have highly reduced a number of communications you need, okay, with this kind of connective communication idea, okay? And in this way, actually, if you think about it, most of the majority of our job is local computation, with only minimal number of communication needed. Then that could really largely reduce the burden on the DQC hardware development. So that's another way I'm saying, like, even though like we are working on the software part or architecture part, we can really lead into like giving better guidance for the hardware people to let them know what is needed there. So here, just want to give you a summary and high-level takeaway. So even though like our work of emphasizing on the compiler part, similar philosophy can be applied to architecture design and programming language, which is the other important research topics in our group. But generally speaking, even you are not working in the quantum computing world already, your classical expertise could help you survive here. And a lot of high-level philosophy really provides a direction. Try to follow like the key philosophies you have learned in classical computing will be very helpful. And the last slide is just to show, okay, another important part of my research is ML, machine learning systems. And again, like especially we are focusing on the performance optimizations and without harming the programmability. And we are ranging over a lot of system stacks from the algorithm to kernel optimization to compiler runtime and hardware accelerator designs, and for a lot of different machine learning models. And recently, our group is also focusing on the large language models optimizations with a lot of system optimizations. And if you are interested in that directions, you are also like feel free to contact me. And that's all for today's talk. And another thing is our group is actively recruiting like PhD students. So we have at least 2 openings for ML system and 2 openings for quantum computing systems. So if you are interested, you can shoot me an email and we can discuss offline. Thank you for coming to my talk. Any questions?